Okay, so today what we're going to talk about are systems of equations, okay? We've spent a lot of time working with systems in terms of linear systems, okay? But now we're going to kind of step that up a little bit and talk about systems in terms of some of the conic sections that we've been studying. So let's just review real quick. If I had a system of linear equations, how many possible solutions are there? If I have a system of linear equations, how many possible solutions are there? If I have a system of two equations, you can have two. You can have one solution, right? That's one chance. That's one thing. What else could happen? Okay, you could have infinitely many, or you could have none. Okay, so there's basically, if you kind of want to say, there's three possible outcomes, right? One solution, no solution, or infinitely many solutions. Okay, so what we're going to do is with these different types of conics and lines is we want to kind of figure out what the possibilities are. So let's look at number 1. X equals y squared minus 3, and 3x minus 6y is equal to negative 12. Okay, look at that top equation. What type of graph is this going to end up being? A parabola, good. What type of graph is the second equation going to end up being? What? Linear. How do we know it's linear? Yeah, nothing's being squared. In a parabola, there's one squared term. In a linear graph, there's no squared terms. All right, so let's think about this. This parabola is facing horizontally because it's a y squared. So let's think about the different possible number of solutions. So let's start with none. Is there a way to have no solutions with a parabola and a line?
No. Yes.
Yeah. What if I drew my line something like that? It would have no solution, right? Okay, so no solution is a possibility. Could we have... Well, think about the directions they're going. This one's sloping up at this rate. This one's sloping way out at a far different rate. So they're never going to hit. Okay. All right, could we have one solution? Yeah, what would that look like? Yeah, we could have the axis of symmetry. Okay, you could also have a line that is tangent to your parabola, right? Hits it at just one point. Okay, so we can have one. Could we have two solutions? Yeah, what would that look like? All right, it could go through like a secant line to this parabola. Could we have three solutions?
If the line is like, oh, no.
Yeah, we're not going to be able to hit three solutions. 0, 1, or 2 solutions are possible. All right, so let's see if we can solve for our solution points. We're going to practice some of our previous methods of substitution and elimination. Number 1 is set up very nicely for which process? Substitution. We already know that x is equal to y minus 3. Sorry, y squared minus 3. So I'm going to take that and I'm going to plug it into my second equation. So I'm going to have 3 times y squared minus 3 minus 6y is equal to negative 12. All right. At this point, I would distribute. So I would have 3y squared minus 9 minus 6y equals negative 12. Okay. Actually, this is a quadratic. So what do we like to get it set equal to? 0. So I'm going to add 12, and I'm going to go ahead and rearrange this. All right, this is 3y squared minus 6y plus 3. All right, now when we solve the quadratic, the first thing we always look to see if we can do is if we can pull out a GCF. Can we pull out a GCF here? Yeah. So I'm going to pull out my 3. I'm going to have y squared minus 2y plus 1. All right. The easiest method to move forward here to solve this is to use factoring. So does y squared minus 2y plus 1 factor? Yes. We need the factors of positive 1 that add up to negative 2. Negative 1 and negative 1. So y minus 1 times y minus 1. Okay. Once you factor, what do you do?
Set each factor.
Good. Set each factor equal to 0, which in this case is going to give us the same solution. It's going to give us that y is equal to
3.
1.
What's the 3?
Well, if you try and set 3 equal to 0, it doesn't work.
But could you say 3y?
Nope. 3 is a separate factor, so you think about setting 3 equal to 0, but that does not give you a solution. All right. Once you have what y is equal to, what do we do with it?
Plug it back in.
Yeah, plug it back in to find x. So once I know that y is equal to 1, I want to find x. So x is equal to 1 squared minus 3, which is negative 2. So what is our solution? Good, negative 2, 1. Questions on that one?
Would it be 2 solutions if the y was like, if it was 1 minus 3 and y plus 3?
Yeah, so if we got 2 different y values here, we would plug each one in and get the x that goes with it.
Is that the 2 solutions?
That's what 2 or more solutions would look like, yeah. Okay, let's look at number 2. X squared plus 25 is equal, or sorry, x squared plus y squared equals 25, and y plus 5 equals 1/2 x squared. So what is our top equation? A circle. Good. How do we know? Good. Their coefficients are exactly the same. Coefficients have to be exactly the same in a circle. What is the second equation? A parabola. How do we know that's a parabola? Only one squared term. All right, so we've got a circle and we've got a parabola. Let's think about how many possible solutions we could have. Is there a way to have no solutions in this situation? Yeah, what if my parabola opened down? Yeah. Or what if it opened up and just was on the outside of the circle? Lots of options. Okay, so definitely we can have 0 solutions. Could we have 1 solution? Yeah. We could have a vertex on the circle, right, and open down. We could have a tangent. Oh, not quite tangent, but we could have a tangent to it, right? Go like that. Okay, we can definitely have 1 solution as well. Could we have 2? What would that look like? Okay, you could have tangent on either side. Yeah, you could have a vertex in the middle. Have 2 solutions that way. You could have just a vertex out here and 1 branch go through, right? And the other one come out here. We could definitely have 2 solutions. Could we have 3? Yeah, how could we have 3? Good, we could have our vertex on the circle. And then intersect it both ways there. All right, so we could have 3. Could we have 4?
Yes.
Yeah, how could we have 4? Yeah, we could have our vertex outside. You can go up here and up here. Oh, that one kind of looks tangent, sorry. It's like that. Could we have 5? No. 4 is the max. So you can have 0, 1, 2, 3, or 4 solutions. We don't know how many we have until we were to either graph or as we're doing solve algebraically. So let's go ahead and solve this. First thing I'm going to want to do is get rid of this fraction in my second equation. Yeah, let's clear our fraction by multiplying everything by 2. So now that gives me that 2y plus 10, is equal to x squared. So what I'm going to do is I'm going to take that and I'm going to plug it in up here for x squared. All right, so let's see what we would have. We would have 2y plus 10, because that's replacing our x squared, plus y squared is equal to 25. Everyone okay with that? All right, now we have a quadratic. We have 1 squared term, so we're going to get this set equal to 0. So I have y squared plus 2y minus 15 is equal to 0. Okay, let's see if this will factor. We need the factors of negative 15 that add up to positive 2. So we're going to have y minus 5 and y plus 3. Oh, yeah, sorry. Y plus 5, y minus 3. All right, so what 2 y values does that give us then? All right. So what we do from here, and I'm going to kind of go into this next, so don't write this one down yet. What we do here is we take each of these y values and we plug them in. Okay, so let's start with y equals negative 5. I'm going to go back to this equation for x squared, and I'm going to plug in y equals negative 5. So x squared is equal to 2 times negative 5 plus 10. So 2 times negative 5 is negative 10. Negative 10 plus 10 is 0. So if x squared is equal to 0, what is x? 0. So what solution have we now created?
0.
Yeah, 0, negative 5. All right, let's try with 3. X squared is equal to 2 times 3 plus 10. So x squared is equal to 2 times 3 is 6, plus 10 is 16. To solve this, we take the square root of both sides. And what do you have to remember when you take the square root of both sides? Plus or minus. So x is equal to plus or minus 4. So we've now created 2 more solutions. Okay? Positive 4, comma 3, and negative 4, comma 3. So our final answer would be these 3 solutions. You can write them in a solution set. 0, comma, negative 5, 4, comma 3, negative 4, comma 3. And that's your answer. We wouldn't know exactly which case of 3 solutions this would have until we graphed it out. But algebraically, we now do know where those locations are located. It doesn't really matter. All right, go ahead and copy down number 3, please. Okay, what is the top equation going to be?
Like,
Circle.
oh,
Not a circle,
ellipse.
an ellipse.
Square.
Same sign, different values. Okay, what is the second equation going to be? A hyperbola. How do we know?
Different sign.
Different signs. Okay, I promise you guys, you will be asked to identify conic sections on the test just from the equation. Okay, you've got to start pulling together all those different rules that we've talked about so you can look at them really quickly. It should take you seconds. Okay, so start practicing that. All right, I'm not going to try and draw this out because we've only studied very specific cases of ellipse and hyperbolas. We've studied perfectly vertical and perfectly horizontal. There are all kinds of ellipses and hyperbolas that are slanted. Okay, so I'm not going to sit here and try, while these are both vertical and horizontal, I don't want to try and draw all the different possibilities of their intersections because I think it would get kind of weird. Okay, but there are between 0 and 4 possibilities. Okay. All right, so I don't think this one is really well suited to substitution. What method would be best for this one? Elimination. It's all set up very nicely for us. Okay, so my 9y squareds are going to be eliminated. And I'm going to end up with 41x squared is equal to 369. If I divide both sides by 41, I'm going to get that x squared is equal to, sorry, I'm supposed to answer that. X squared is equal to 9, which means x is equal to what? Good. Don't forget your plus or minus. When you write in the square root, you have to remember your plus or minus. So x is equal to plus or minus 3. All right, so we're going to take each of those, and we're now going to plug them in. So let's,
I said, whatever we plug it into, so we don't think.
I'm not sure I understand what you're saying.
You can simplify it like there's a. Never mind. I was just.
Okay. I always pick the equation with the smaller coefficients just so it's a little bit easier. Okay. So I'm going to put this into my bottom equation. So I'm going to have 16 times 3 squared minus 9y squared is equal to 144. Okay. So order of operations, we square first. 3 squared is 9. 9 times 16 is 144. So that works out very nicely. It allows us to cancel out these 144s. And we have that negative 9y squared is equal to 0. What does that mean about y? Y would have to be 0. Good. Okay. So what ordered pair does that give us? 3, 0. All right, so let's think about this. If we were to start and plug in this negative 3, what's going to end up happening? Yeah, it's going to be the exact same because when I square negative 3, again, I end up with 9, right? And 9 times 16 gets us back to this 144. We go through the process. We get, again, y is 0. So what ordered pair does this create? Negative 3, 0. There are 2 solutions for that situation. Okay, sorry if you've already started writing this, but I didn't realize that this class period was a little bit shorter than the other ones. So yeah, I don't like that they're uneven like that. But I want to make sure we get to these next few. So let's go ahead and skip to this number 5, please.
Period at 50 minutes and first period at 45.
And then the afternoon period's only at 40.
And they got the alarm
The bell rings at 2:40. All right, So look at number 5. What is the top equation going to give us?
It is
Ellipse.
Ellipse. Why is it an ellipse and not a hyperbola?
it equals 1.
The addition. Good. The addition. What is the second equation?
Linear.
Line.
Linear. Good. All right. First thing I want to do here is I want to get rid of these fractions. So what could I multiply the top equation by that would clear all of my fractions? 30. Good. So if I multiply my first fraction by 30, I get 30x squared over 30, which is just x squared. And then if I multiply the second fraction, what am I going to get?
Y squared.
Good. 5y squared is equal to 30.
Oh.
And I have my other equation, x equals y. All right, so you can plug in here for whichever you want. You can either plug in for x or you can plug in for y. It definitely does not matter. But either way, you're going to plug in. So if I plug in for x here, I'm going to have y squared plus 5y squared is equal to 30. So that gives me that 6y squared is equal to 30. So y squared is equal to 5. So what's y equal to?
Positive root square root of 5.
Good. Plus or minus the square root of 5. All right. So if y is equal to the positive square root of 5, what must x be?
Oh, no.
X is equal to y.
So square root
Yeah, so x has to also be root 5. So what ordered pair does that give us?
of 5 is 9.
Root 5 comma root 5.
Positive negative.
Well, it's specific that the positive x value has to go with the positive y value because x has to be equal to exactly root 5. X has to be equal.
And then when
X has to be equal to y. So if on another one we let y be negative root 5, then what's x? Negative root 5. So these are your two ordered pairs, but you can't mix them up. Only the positive goes with the positive and the negative goes with the negative because they have to be exactly the same. Okay. Questions on that one? Okay. Let's talk about inequalities for just a moment. All right, if we try and go back and think about linear inequalities, okay? With a linear inequality, we have to decide a couple things. First, we would have to decide if our line is solid or if it was dotted, right? And then we have to decide if we're going to shade above or below. So I could have that line, and then I could have, say, another one that's dotted, and I shade below on that one. What is the solution to this system?
double shaded.
Yeah, the double shaded area. So this area, right? Okay. Same idea here. We're going to decide solid versus dotted, and we're going to look for our shaded area that's double. Okay. So look at this. We've got a parabola, and then we've got a linear function. So let's start with this parabola. X squared plus y is less than or equal to 3. Because this is so simple, I'm going to use transformations to graph this. So y is less than or equal to negative x squared plus 3. So that is a reflection across which axis?
Y.
The x-axis. And we're going to go up 3 units. Okay, so I have points here. I use my parent function rules because there's no stretches or compressions. This is going to be a solid parabola because of the equal to. And because it's less than, we shade below the vertex. Bless you. So we find our vertex and we shade below it. Okay. then we take our line, our linear function. So negative y is less than negative x minus 1. So y is, we would just multiply everything by negative 1. So y is greater than x plus 1. Is that one going to be solid or dotted? Dotted. So y-intercept of 1, slope of 1. It's going to be dotted. And which way are we going to shade? Y is greater than, so we shade above. So your solution is this region right in here where your shading overlaps. Okay? Okay. The next one deals with ellipses and circles. Okay. What you need to know about ellipses and circles is if your equation is less than 1 or less than r squared, you're going to shade inside the graph. So like inside the ellipse or inside the circle. Okay? If your equation is greater than 1 or greater than r squared, you're going to shade, where do you think? Outside. The same rules apply for solid and dotted. Okay? All right. I'm going to show you what this picture looks like real quick because we're not going to have time to get there. So give me 2 seconds just so I can talk you through it real quick. All right, just look real quick. Here we shaded outside our circle, but inside the ellipse, so the intersection was in those two regions. Okay? So you still plot your center and your vertices and co-vertices, or your center and your radius, and then do your shading. Okay? I need to give you your homework real quick. Sorry.